This is Geometry, Note Section 2.1, Inductive Reasoning. We are trying to take the concept of inductive reasoning in order to lead us to a point where we can do one of the hardest things in mathematics, which is proofs. Inductive reasoning. Looking at several specific situations to arrive at a conjecture. Well, what's a conjecture? That's an educated guess. So you're educated. You make a guess based on that education. That's a conjecture. Another term, counterexample, a false example, an example that proves a conjecture false. We will get into this, I think, towards the end of the notes. Right now, let's focus on inductive reasoning. Use inductive reasoning to conjecture about the next two numbers in the pattern. So looking at these numbers, we have 1, 4, 16, 64. What do you think's happening with these numbers? I think that we can conclude that if we multiply each number by 4, we're going to get the next number. 64 times 4 is 256, and the next number is 1024. Our conjecture is the next two numbers are 256 and 1024. Is that actually the next two numbers? We don't know for sure. There could be some kind of a bigger, more complex pattern in this, but it sure appears if we multiply by 4 each time, we're going to get the next number. Number 2. This wouldn't be, the direction said use inductive reasoning to conjecture about the next two numbers in the pattern. How about the next two objects in the pattern for this? So something that I could easily conjecture about right now is that the next shape is definitely going to have a circle involved in it, because each of these have a circle. So that's fair for me to conjecture. And then looking at the first shape, it's a triangle. It's got 3 sides. The next one is a square. It's got 4 sides. Then a pentagon. It's got 5 sides. I think it's reasonable to assume that the next shape is going to have 6 sides, which is a hexagon. One after that is probably a septagon as opposed to a diseptagon. 1, 2, 3, 4, 5, 6, 7. So our conjecture is that each shape is a circle, and inside of it, it's called inscribed. The polygon is inscribed, the circle circumscribes it, has one more segment than the previous one. Number 3, so the first shape is a circle, and it looks like the next shape is the same circle, but then inside it at the top is a circle that's half the diameter of the previous one. And it looks like the next shape is those two circles plus another circle that's half the diameter of the smaller circle. So it seems reasonable to me that this next shape is going to be 4 circles. And the next circle is going to be half the size of the previous circle. And then I think it would be reasonable to assume that the next shape is going to have another circle inside that circle, half of its size. Can't draw one that small. There we go. Conjecture, an educated guess. Number 4, we're back to numbers. What's happening with these numbers? Looks like they're being cut in half. Like we divided by 2 to get from 16 to 8 to 4 to 2 to 1. I don't like dividing by 2. It's easier for me to multiply by a half, which is the same thing as divided by 2. So 1 times a half is a half. A half times a half is a fourth. When you multiply two fractions, you multiply the top numbers together and the bottom numbers together. Number 5, how many dots in the 20th figure? Now this just became a lot more complicated because it doesn't ask us to figure out what the next two patterns are, it's asking for the 20th. So this is figure 1, figure 2, figure 3, figure 4. We don't want to have to draw 16 more of these shapes. So can we figure out, just looking at this, what this pattern is? What if I were to tell you that the first one is 1 squared, the second one is 2 squared, the next one is 3 squared, the next one is 4 squared. So the 20th figure would have 20 squared dots. Now, if you want to multiply 20 times 20 and get 400, you can do that, or you can just write it as 20 squared. That is cool with me. Number 6, try to figure out the 43rd term in the following sequence. All right, so sequence, is this repeating itself? Sure looks like it. A, E, I, O, U. A, E, it's probably I, O, U. There are 5 numbers in this pattern. Since there are 5 numbers in this pattern, not numbers, 5 letters. And then it repeats itself. I'm going to show you a method that you could use to figure this out. And there's lots of different ways to think of this. If you don't like what I'm going to say, and you have a way that you like better, that's cool as well. Since there's 5 numbers in the pattern, I'm going to take, this would be the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. I'm going to take whatever number I'm on and divide it by 5. Old school division. 5 goes into 1 0 times. 1 times 5 is 0. What's my remainder? Remainder is 1. Let's focus on the remainder. So if I take and divide 1 by 5, the remainder is 1. If I take 2 and divide it by 5, that also goes 0 times. The remainder is 2. If I take 3 and divide it by 5, goes 0 times. The remainder is 3. Hopefully you can see what's happening here. The next one's going to be remainder 4, then a remainder 5. Well, I shouldn't say that. When you get to the 5th one, I'll just write this down. If you divide 5 by 4, it goes 0 times remainder 4. If you divide 5 by 5, it goes 1 time evenly, the remainder is 0. Once you get to 6, where this pattern's repeating itself, if you take 6 and divide it by 5, it goes 1 time, the remainder is 1. Notice how A always has a remainder of 1. Because the next time you'd have an A would be 5 more than 6, which is 11. 11 divided by 5 goes 2 times, remainder 1. Every time E appears, the remainder is 2. Every time I appears, the remainder is 3. Every time O appears, the remainder is 4. Every time U appears, the remainder is 0. So to figure out what's happening on the 43rd term, we're going to take 43 and we're going to divide it by 5. 5 goes into this 8 times. More importantly, what's the remainder? The remainder is 3. We are expecting the 43rd term to be an I, because every time you have an I, the remainder is 3. You probably noticed in the last 2 problems, I wrote sentence answers. There are times when sentence answers are appropriate, and most of the time that's appropriate when the problem is a word problem. That's a problem, it has words in it. Give a counterexample for each of the following, for each of the false conjectures given. So here's what happens with a counterexample. A counterexample has to make the hypothesis, which we haven't learned what that is yet, but we will here shortly, makes the hypothesis true, and it makes the conclusion false. If the name of a month starts with the letter J, it is a summer month. So can you think of a month that starts with J, but that's not a summer month? Sure, how about January? January is a counterexample. It makes the first part of the statement true, that's the hypothesis, makes the conclusion false. Let's check out number 2. Multiplying a number by -2, so we want this part to be true for a counterexample, makes the product negative. We want this to be false. So can you think of a number that you can multiply by -2 and the result is not negative? Sure. If I take -5 times -2, that's going to be a positive 10. This is a counterexample. The counterexample is the -5. Well, you don't have to use -5. Any negative number works. Also, if you were to multiply by 0, that would work as well, because 0 times a negative is 0. We found a number, we multiplied by -2, and the product, the answer to multiplication, was not negative. Trying to make the initial part of the statement true and the final part of the problem false. If you teach geometry, you are bald. Well, are there any teachers at Indian Valley that teach geometry and are not bald? You betcha. Sweet Mrs. Allensworth. She teaches geometry, that's true. She's clearly not bald, so that part's false. All right, on to the back. Got a little bit of this pre-filled in just to save a little bit of time. Not going to save much time. Conditional statement. A statement that can be written in if-then form. Notice it says can be. You don't have to write it in if-then form, but if you write it in if-then form, it makes it more obvious about what's happening. 1, write a conditional statement. Write a conditional statements. It's a typo here, my apologies. So what I wrote, if you are in this class, then you are in geometry. No one said your conditional statement has to be true, but in this case, if you're reading this and you're in this class, you are likely in geometry. That's a conditional statement. Hypothesis. The portion of an if-then statement that immediately follows if. So in this example, you are in this class. That is the hypothesis. Conclusion. The portion of an if-then statement that immediately follows then. What follows then? You are in geometry. Please note, technically, the words if and then are not part of your hypothesis and conclusion. And I will likely count it wrong if you do include it. Let me give you a little bit more here before we move on with this base example. Conditional statements can be written symbolically by writing a letter, arrow, a letter. Here's what that means. P implies Q. That's how this is read. P implies Q. So in the example that we just gave, if you are in this class, then you are in geometry. P in this case is you are in this class. Q in this case, you are in geometry. P implies Q. So in number 2, this is what P is, the hypothesis. And number 3, this is what Q is, the geometry. All right. Once again, I wrote this down already just to save a little bit of time on this video. Write the following in if-then form. Adjacent angles have a common vertex. So the original thought is that we have these adjacent angles. Now, how many angles do you think this problem is referring to? It's implied but not said. I would think this is referring to 2 angles. It could be more, but let's just say it's 2 angles. So I wrote this first part as if 2 angles are adjacent. Different wording than this, but same concept. Conclusion, then they, what are they? The 2 angles, have a common vertex. So in this problem, this is my P, and this blue part is the Q. P implies Q. Number 5, vertical angles are congruent. How many angles are vertical? 2. So if 2 angles are vertical, that's this first part, then they being the 2 angles, are congruent. Once again, this is P, and it is implying what's in blue, which is Q. Converse. A statement made by interchanging the hypothesis and conclusion. Write the converse of the conditional from number 5. When you write this converse, you cannot ignore the English language. So here's what I mean. This is wrong what I'm going to do. I can't just take what's in red and move it down here, and take what's in blue and move it up here. So why? Why is that not great? Because I start out my sentence if they are congruent. We don't want to use a pronoun unless we know what the pronoun is taking the place of. So I want to leave the 2 angles up here. So a better way for me to write this is if 2 angles are congruent, then they are vertical. Conceptually, I interchanged my P and my Q. Grammatically, I didn't interchange every single word of it. Once again, the original statement, if 2 angles are vertical, then they are congruent. I'm saying if 2 angles are congruent, then they are vertical. A converse statement, if the original one is P implies Q, is Q implies P. Notice once again, no one said anything about this being a true or false statement. I mean, we can get things being true or false, but you can write the statement and it be false. Inverse. A statement made by negating both the hypothesis and the conclusion. Here's what this would look like symbolically. Not P implies not Q. One cheesy poof in this context means not. Cheesy poof. Write the inverse of the conditional you made for number 5. So let me cheat on this again because let's be honest, that's how I was raised. I was raised to be a cheater. That's not true. Marvel would slap me in the face if she heard me say that. So I just wrote down statement 5. I haven't changed anything yet. So the inverse is negating the hypothesis and conclusion. How do I negate something? Well, I want to say if not P, so I want to say if 2 angles are not vertical, then they are not congruent. Symbolically, I'm saying not P implies not Q. If 2 angles are not vertical, then they are not congruent. Contrapositive. A statement made by negating both the hypothesis and the conclusion of the converse statement. Well, the original statement was P implies Q. The converse is Q implies P. So the contrapositive is not Q implies not P. So if I take the statement I made in number 5, if 2 angles are vertical, then they are congruent. And if I take the converse to that, which is a statement I made in number 6, and I negate both of those, it would be if 2 angles are not congruent, then they are not vertical. Not Q implies not P. All right, we're almost finished. this chart could be valuable to you. The contrapositive will always have the same truth value as the original conditional. The converse and inverse might have the same truth value, but it also may not. So if your conditional statement is P implies Q, which you could write if P then Q, if that's true, then the contrapositive is also true. If the conditional statement is false, then the contrapositive has to also be false. Who knows what happens with the converse and inverse? If you notice, the inverse is the contrapositive. Oh, that's just getting wordy. That's just getting wordy. All right, please do the homework as noted on the website.